Well, hello geometry students and welcome back to Honors and Gifted Geometry. I'm Mrs. Arp and I'll be teaching you 2 lessons today. We're going to be getting started into chapter 11. So if you haven't already downloaded and printed your 11 notes or your 11 1 and 2 this week for the reteaches, you can go ahead and do so. Remember, you can stop the video at any time if I go too fast for you. And also remember, you can call and contact your teacher anytime you want. So I hope you had a very great weekend and got all your work done by Friday. So again, this is the work for the entire week. And so you'll have the same kind of setup as we did last week. We'll be doing some problems on the reteaches. That'll be as a separate video. And then there'll be the problems from the audit sheet. The audit sheet now is online, so just like you had from before, you'll see where your homework audit sheets are. You'll need to print out, and we'll do just 11-1 and 11-2 this week. Okay, so I hope everybody had a great weekend and you got a lot of time to go walk your dog. I didn't walk my pet at all, but he's out here to remind me we have a joke. Oh yeah, a little pun here. So what's the question for the week? The question this week is, well, we're going to be working with solids. So, what solid can cure a strep throat? What solid can cure strep throat? Think about that this week, and you can discuss it or whatever in the discussions here. Let's go ahead and get started on chapter 11. Okay, in chapter 11, we are looking at just a few notes here. So first of all, we are talking about spatial reasoning in chapter 11. So it's all about volume and stuff looking at spatial reasoning. 11-1 is looking at solids. And most of you are pretty familiar with the 4 kinds of solids that we'll be studying. We have one other solid in the last section that we'll add to it. But the solids made from 2 congruent bases would be prisms and cylinders. Because they have 2 congruent bases and all of their lateral faces would be rectangles. And then if they only have 1 base, okay, that would be your pyramids and your cones. They just have 1 base. They have 1 point opposite that 1 base. That point is called an apex. So if I refer to that, that's what that is. But the first thing we just want to do is the basic vocabulary. So you can see the solids are named by their faces. So you're looking at their bases and their faces. So first of all, let's kind of figure out that vocabulary. So let's just take a look at this solid. So what we have here has 2 congruent bases, okay? And these lateral faces are all rectangles. So this would be called what? That's right, a prism. A prism is anything with 2 congruent bases and lateral faces is rectangles. All of the polygons themselves, anything that you can touch, are called the faces. So when you worked with surface area before, that's what they're talking about, is this, the faces would be all the surfaces. So every face is surface area. Bases are the 2 congruent ones. Lateral faces are the ones that are not bases. So essentially, you have lateral faces plus bases would equal all of your faces. So here we would have 8 different faces, okay? So if we had just a rectangular prism, you'd have 2 rectangular bases and 1, 2, 3, 4 lateral faces for a total of 6 faces. So lateral faces plus bases equal your faces. Okay, then we also talk about edges. So they'll ask you to name edges. Well, edges are just like what you would think, the edges of the pyramids or cones or whatever we're working with. So here we've got segments. So if I looked at the edges, I would have 4 edges on the top of this rectangular pyramid or prism. I'd have 4 edges on the bottom of this rectangular prism, and then 4 going up. So I'd have a total of 8 edges here. When we move into pyramids, we still have bases, but there's only 1. So we'd have 1 base, and notice now that our lateral faces turn into triangles. So in pyramids, you're going to have 1 base opposite the apex, and then all my lateral faces. But again, total together, 1, 2, 3, 4 faces together. My edges, there'd be 3 edges on the bottom and 3 edges coming up to the point. So this would have a total of 6 edges. Then another vocab word you have is vertex. The vertex or the vertices are just like you would assume. It's going to be the corner point. So we have faces, edges, vertices in every one of these solids. Okay, and then we had the cylinders. A cylinder would be like your cans of soup that are in your cupboard. Okay, and so my edge here is actually going to be the circumference of the circle. Okay, so we really don't have edges in a cylinder, so to speak. But we do have what we call a net. A net is simply taking the shape and making it flat. So what shape would this be? I just got out of my cupboard and emptied it. It is a cylinder. A cylinder then is made of 2 congruent bases. So I've got my 2 congruent bases. And now what shape would the lateral face be? Well, you guessed it, it still has to be a rectangle. Notice that the rectangle, the height of the rectangle is just like it would be for any rectangle, but the length of the rectangle gets put into and makes the what? Circumference of the circle. So we're really looking at circumference times height for the area of this rectangle. So kind of keep that in mind as you do your homework here. Okay, so we have a net is just flattening the surface out and making it 2-dimensional. I do want to point out that you don't have to make nets exactly the same way. Wait, he has the answer to the joke. Well, you gotta wait. You can't give it out so far. You remember what solid can be used to cure strep throat. Okay, so what I'm getting here is just an example of another net. A net just takes these shapes and cuts them all out. So you can see I have 1, 2, if I put it back together, 3, 4, 5, and at the bottom 6 in this prism called, whoa, there you go, called the Cheerio box. Okay, and so you would have a net just flattening it out, but notice when you flatten it out, you do have to keep all of the polygons connected. My point in this is you don't have to make the same net. So this could be the exact same Cheerios box, but the net is different than this one, okay? So I kind of cut it out this way. So you have to kind of look at the net and decide what is it that's going to be put back together, what is it going to make. So there's not just one net. And the last thing I want to talk about is a cross section. A cross section is simply going to be just taking any plane. So remember, a plane is just a flat sheet of paper and saying, okay, I'm going to cut through the shape. So I've got my 3-dimensional, let's just look at a cone, and I cut through the shape. Well, I could cut through the shape and just go all the way around. And of course, that would be similar to the shape on the bottom, and I would still have a circle. So a circle would be one of my cross sections. I could also then slant it instead. So if I slant it, instead of going parallel to the base, and I just slant it instead, I no longer am going to have a circle. What shape am I going to have here? It almost looks like an Easter egg, doesn't it? But that's called an ellipse. So you could have a cross section that's a circle, a cross section that's an ellipse. You could also have a cross section that is parabolic. If I just go straight and cut right down, do you see how you'd have a parabolic shape? So I have a parabola. There's a fourth one that actually takes 2 cones, and that's called a hyperbola, and those are your conic sections. You'll study more of those in Algebra 2 and beyond. But you had the parabola before, you've had a circle before, we had the ellipse, and then if we have another one, double helix it's called, it would make it a hyperbola. And the last conic section is what happens if you go right straight down the middle. If you go right straight down the middle, Well, that's a shape we studied over and over again. You got it. It's just a triangle. You see how we got the triangle in there? It's kind of hard to see with the glare there. Okay, so those are all conic sections. Obviously, you could do cross sections with any shape. So I could make a cross section of a cone or of a cube. If I say the cross section of a cube, I could obviously make it into a square, but it wouldn't have to be a square because I could cut through this side and come out on this side, and that would make it a rectangular cross section. So you're just really looking at the polygon named for your cross section. So your vocab then for 11.1, and again, you can stop the video at any time, so you can copy it all down. We've talked about faces, which comprise of the lateral faces and the bases, the edges, which are the segments, the vertices, the points, the net, just cutting it all out into 3 dimension, and the cross section where you've got actually a plane that cuts through it, okay? So the last thing I want to talk about in this section is how do you draw one of these 3-dimensional figures. I want you to be able to draw a cube. So to draw a cube, it's not too bad, and you should be able to draw any rectangular prism. You just start off with any square, and then just start in the middle of your square and make a congruent square. So you should be able to draw cubes for your homework here and on the homework assignment. Then I just connect my vertices, and I have a cube. Remember that to help you to see more 3-dimensionally, that it will sometimes have dotted segments. And if you can kind of push those dotted segments into the back, that would make it more 3-dimensional to you. Okay, now let's take a look at this cube, and let's just see if we can review those vocab words. How many faces would that cube have? Remember, faces are every side. So yes, you're exactly right. It would have 6 faces. How many vertices does that cube have? Well, vertices would be all the points. You got 4 on top, 4 on bottom. So yes, you have 8 vertices. How many edges does this cube have? Edges, remember, are just the segments. So you'd have 4 on the bottom, 4 on the top, and then 4 that connect, as we told you earlier. So you'd have 12. Now, do you see how somebody a long, long time ago, and much smarter than me, named Euler, decided, hey, there's a relationship every single time on any of these solids. And you can kind of see that relationship if you just look at it in terms of a cube. So it's not really anything you have to memorize. If you just look at the cube, you can get it. You can say, oh, I've got 6, and I've got 8, that's 14, and I've got 12, well, I have to add 2 more to it, and I'd end up with 14 equal 14. So Euler's formula is what it's called. I know it looks like Euler, but it's pronounced Euler, is simply faces plus vertices is equal to edges plus 2. So you'll need that for your homework, and I'll show you more examples of that on the reteach video. The reteach videos will be available to you on another video like they were last week. Okay, that's basically 11.1, a lot of just kind of review for a lot of you, hopefully, and 11.2 is probably easier than harder. Okay, 11.2 is saying let's find volume. So 11.2 is just volume of prisms and cylinders. Oh, he's been waiting patiently. He wants to know what is that, what solid, what solid. Go sit down for a while, wait. We can figure out what solid would cure strep throat. You can just put that on the discussion board, right? Okay, so volume is equal to base times height. This is a formula that's actually on your reference sheet, but we are no longer using the reference sheet because we don't have to have that in the course exam. Woohoo! A capital B stands for the base area. So it's very important to understand that it's not just one length. Capital B is the area of the entire base. So you see how we're getting into 3-dimensional. And of course, H stands for the height. So if we were going to do a real easy find the volume of a cube that was 5 inches on each side, then I would simply say my base is one of those, either the top or the bottom, just one of them. So it's a square. 5 by 5. So my base area would be 25 square inches. Now when I multiply 25 square inches by the height, which is exactly the same as the 5 by 5 because it's a cube, then I'm going to have 5 inches times 25 square inches, and that's how we get 125 cubic inches. So all volume is in cubic units. So we just write that with our units into the third power. Let's try one example here. Let's say we have find the volume of a cylinder. If I have the base of the cylinder is 121 pi square inches, and the height is 1 foot. So we're looking at that, we're saying the area of one base, oh, we already have that. And now the height is 12 or 1 foot. So we have to worry about that because this is in inches and this is in feet. So in your assignment, make sure that your base and their height are in the same units. So all I'd have to do here is take my base that was given to me, 121 pi square inches, and multiply it by the height, 12 square inches. And if we wanted an exact area, we would of course leave the pi to be exact, and we'd say 121 times 12 are 1,452 pi cubic inches. So remember, you're going to be looking at cubic inches. Make sure that's a 3. Okay, and remember that you're going to leave the pi for exact. If on the homework it says to round, then you would just simply multiply it by pi, or by, pi and round it. Okay, one last thing in 11.2, and I think it's pretty much like the reteaches, so we'll get to those here in just a little bit. But we have this guy named Cavallari. I know, it's kind of like, reminds me of the deli, Cavallari's Deli, but it's not that. Cavallari had a principle that said, if I have any cylinder, it won't matter if it's slanted or not, okay? As long as it's a cylinder or a prism, I can slant it and it would still have the same volume. I think it's easiest to picture Cavallari's principle using coins, and all of mine just dumped over here. But if you have all of these coins just standing straight up, so I found the most pennies, what shape would that make? You're exactly right, that's just going to be a cylinder. So if I have that cylinder, would it change volume if some of the coins were coming out this way and some of them that way, and it ended up being crooked? Nope. Every cross section would be congruent still to the bases. So as long as you have congruent bases or congruent cross sections for the bases, it's still going to be base area times height. Now you do have to be careful. So Cavallari's principle is saying as long as I have the same cross section, but what happens if I slant? Now my height is no longer a side, it's the one that's perpendicular to the base. So assume these were the exact same size circles. My base then would still be my circle, but my height moves out because my slices are all congruent. That's Cavallari's principle all the way through. So it would still be volume equals base area times height. But you have to be careful, the height might be on the outside. Okay, that's really the nutshell behind everything in 11.1 and 11.2. I'll work a few problems for you on another video for the 11.2 and 11.1 reteaches. And I hope that you've learned something or at least had a good review. We're going to do the same thing this week as we did last. You'll be finishing the reteaches, 11.2 and 11.1, just the ones I do on the video. And then send those in to me, and then do the 11.1 and 11.2 audit homework. It's all from the textbook. The audit sheets are online. There has been one glitch so far, and that is that the submissions, we're uploading them, but it's hard to get them downloaded. So if you could just send me a picture of them via email, I'll get you the points for those. And if you don't have points for last week's, email me or call me, and let's make sure we get that all reconciled. So don't put off those grades. You're doing a great job. I am so proud of all of you, and I miss you a lot. Okay, you can say goodbye. All right, have a good week. Bye.